That would be the one thing right there in this order with that. Oh, also with that one.
Hey, there we go. Works.
Like a lot of it is what we do in physics. His professor who was an international workshop program. And so this is all like the first cycle of stuff that we did was all of our big one. So it's just gotta come back to the yeah.
Like every time.
The same way.
So if you missed two classes.
I gotta go all this.
Oh yeah, finding each equation.
Three or more classes. He drops you.
Problem solving.
He's like serious. If you have a documented reason why, then that's fine.
With every single.
That's a valid reason.
Yeah, but like.
For the police call. So you there is versions you can figure out the total time it takes because we have hard data that's going consistently at see what velocity.
I don't know.
You find out how long of the time of that whole pursuit occurs. And that's how you put down your total time.
Right. So it's transparency. Take another so they just want I don't think I'll right here.
My Monday, Wednesdays, you're so
The time was awesome.
That's what I'm looking for. Okay. Like next.
Oh, yeah.
And that the opportunity to like. That's all.
Yeah.
What about my academic status?
Yeah.
I want to be like.
Oh, yeah. No, like I'll be here because it's like I just
Not with the foundation.
You know, remember I think my class, my CS class, after like 5 minutes, I was on data.
It is right after 3:03 on my clock. And so I have actually from
Well, like,
10 to 11:15 and then 11:30. I had 2 semesters here. And I really like it.
I mean,
I remember when I was taking it. Why?
Yeah.
Oh, yeah. Feel like the whole math video, I've been on the math side by seeing. Instead of believing it's someone. He doesn't. That's like one.
This one.
Yeah, I think probably like this all is, they're already not using it.
And then it's just like, wait, and that's, guys like, I can't promise anything, but. Yeah.
Yeah, no.
I can be the one.
I'll make it like.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Staying dry. Good, good. Yeah, I was not ready for the rain today. I didn't pack any umbrella or anything,
I
but
like the rain, so
I like it too. Just I don't like it when I'm in the rain. I like it when I'm watching the rain from the inside.
I'll lay out.
Yes, right. That's right. All right, so today is our first, I guess you would say, real lecture for EGME 308. So we'll be going over first order ODEs. So this hopefully will be a review for all of you from 250B. So I am going to go fairly quickly, but we are going to try to do as many examples today as we can, right? And as you can see today, this is kind of my normal kind of modality that I use for lecturing. So on Tuesday was kind of a that was kind of a special treat, I guess you can say. I normally don't use slides. I like to use my iPad and I kind of write the notes in real time just because I think it's a little bit more engaging. It gives me a break from talking too. I'm always so out of breath after the first day because I'm just talking through the slides the whole time. But at least this way I can write and talk and write and talk. So it's better for my longevity as well. Okay. Okay, so some announcements. Remember, homework 0 is due this Sunday, so please make sure you send me an email. I think quite a few of you have already sent me emails. I think I'm on top of it as of 3:30, which is when I left my office. But just make sure you get that in before Sunday. The first problem set will be posted soon, so I expect the first problem set will be posted tomorrow. And that's going to cover these first order stuff. Okay. All right. Any questions I can answer before we get started? Yes.
Quick one, do you post these online?
Yes.
Okay.
Well, the written notes I don't, but my lecture notes I post online, and what I write here is basically just a transcript of what's on my lecture notes. But I do post the recordings, and so you can view the recordings on YouTube and kind of go through it that way. Yeah. Mhm. Right. Any other questions?
What's the YouTube channel?
There's a link to it on the it's basically just my personal, it's just a weird combination of it's like Justin Tran and then some numbers after that. I don't, so yeah, but I'll post the recording for the lecture tomorrow. Normally I would have posted the recording from Tuesday's lecture, but we were having issues with the microphone, so I don't think it picked up anything. It's just an hour and a half of just silent slides, which I figure is not the most exciting thing. So today will be the first one that I actually post online. Right, any other questions? Okay, all right, so let's go ahead and get started. All right, so today we're going over first order ordinary differential equations. All right, so really kind of hitting the ground running here. Okay, so first let's just start from the basics. So let's define what a differential equation is. Okay. So a differential equation is basically just an equation that relates a variable along with its derivatives in some kind of structured way. Okay. And so it turns out that, a lot of, physical sciences, the relationship between certain physical quantities, they're related to their derivatives in some way. And mathematically, we can express that with a differential equation. Okay. Let me give you a very simple one. Right. So I think some of you may be taking a heat transfer EGME 407 this semester. And so, one equation that you'll learn is called Newton's law of cooling. Okay. And so Newton's law of cooling is very simple. So if you have some kind of solid surface, right? So this solid surface is at some surface temperature, so we'll call this Ts, okay? And if you have some kind of fluid that's flowing across the top of it, whether that be air, whether that be water, most of the time it's air, right? So these arrows are meant to represent some kind of flowing fluid. So we'll just say it's air to this at this stage. Okay. Okay. This air is usually at some different temperature. And so, we use this equation in thermal capacities to describe, how a part is usually cooled, air cooled, right? So we usually call the temperature of the air, we'll call it T infinity. Okay. Usually the air is a different temperature than the solid. And then we have another variable here called H, which we call the convection coefficient. But for our purposes, you can assume H is just some constant. Okay. Okay. Don't worry too much. Don't worry too much about what the convection coefficient represents. Just assume that it's just some number, like 5 or 6 or something like that. Okay. All right. And so what Newton's law of cooling basically says is that the time rate of change, or the derivative of the surface temperature, is related to the difference in temperature between the surface and the fluid, right? And so the equation for that is basically d Ts dt. Okay. So essentially, this is the derivative of the surface temperature with respect to time. This is equal to minus H multiplied by the difference between Ts and t infinity. Okay. So this is a very simple differential equation here where, you know, our variable of interest here is obviously the surface temperature. Okay. And so this differential equation here basically shows a relationship between the surface temperature and its derivative, along with some other factors, some other properties. So we have the convection coefficient, the air temperature, right? This is a very simple example of a differential equation. Okay. Okay. All right, and so you can come up with, dozens and dozens of other examples from science as well with these differential equations. Okay. All right, let's do a little bit more definitions here. So in this situation where the surface temperature is we call this the dependent variable. Okay? So dependent variable. Dependent variable is usually the variable that you're going to be solving for in a differential equation. Okay. And for our purposes, the dependent variable is usually the variable that's involved in the derivative. Okay. And so if we were to solve this equation here, we'd be solving for an expression for Ts. Okay. Another important factor of a differential equation is the independent variable. Okay. And so usually when we solve these differential equations, we're solving for the dependent variable as a function of the independent variable. Okay. And so in this particular case, the independent variable is time. Okay. Okay. I apologize for the noise. This was kind of an issue last year. There might be a couple times this year where I go next door, I just tell them to shut up a little bit so they get too noisy. But they haven't reached that threshold just yet. Okay. So the introduction of these two variables here kind of brings up an important point. So when we solve a differential equation, we're not looking for a single value. We're not looking for a single number. What we're looking for is an expression, or in other words, we're looking for a function. Okay. And so that's kind of the difference between differential equations and algebraic equations, where algebraic equations, you're looking for just a single value, right? So you have your unknown variables, you're solving for a value. But for a differential equation, you're actually looking for a function. And what that function represents is the function represents how the dependent variable evolves or depends on the independent variable. And so for this particular example here, if we were to solve this equation here, we will be solving for the surface temperature Ts as a function of time. Right, so our solution will look something like this: Ts function of time. All right, so most commonly for independent variables, within engineering contexts, at least, your independent variables are usually going to be something like time or space. And so you'll see T or X or Y or Z a lot. And then your dependent variable is usually some kind of measurable quantity within your engineering system. So like temperature, deflection, voltage, things like that. Okay. Okay, so before we kind of move on to another example, let me just define one more thing while we're here with Newton's law of cooling. Okay, so you'll often encounter extra terms in your differential equation as well. Okay, we'll give kind of a different name to these in a different context later, but since we're talking just purely physical right now, right? Right. So in this particular equation, we have this extra term here, T infinity, which doesn't really fall into either of those categories. And so it's not our dependent variable. We're not explicitly solving for it. It's not an independent variable. We're not, that's not going to be part of our, our solution. But it is going to be part of our equation here. So this term right here, physically, we often call these external forcing terms. And and something like this is kind of the difference between, how I would say like a math person would kind of treat an equation like this versus an engineer who would treat an equation like this, where, usually in engineering or in the sciences, we look at an equation like this, those extra terms there usually represent some kind of physical forcing that's being applied to our system. Okay. In this particular case, our external forcing is coming from the fact that the air temperature is different than the surface temperature. Okay. And so mathematically, those terms will manifest itself, in a different way. We'll kind of get to that in the second half of class today, but I did want to kind of mention that. Okay. Okay, so let's do an example. Right? So let's kind of drive home this notion that when you solve differential equations, you're getting a function. You're not getting a single value. Okay. So let's look at a very simple differential equation. So let's consider the equation x multiplied by dy dx is equal to minus y. Okay. So before we check the solution to this, let's just kind of do a little bit of labeling here. So, from this equation, we can see that y is our dependent variable. Right? It's the variable that's at the top of our derivative. That's what we're going to be solving for. Okay. Whereas our independent variable in this case is x. Okay. And so with that differential equation, we're not going to solve it just because we haven't learned any techniques for solving it just yet today. But I want you to verify. So I'm going to give you a solution to this differential equation. I want you to verify that solution is in fact a solution to this equation. Okay. So I want you to verify. Okay. I'm going to give you this function y of x is equal to 3 over x. Okay. And so we want to verify that this is actually a solution to this differential equation. Okay. So you can see here our solution is an actual function. So it's, a function of x in this case, right? And so to verify this, all we have to do is really just plug it in and just make sure that equation is satisfied. Okay, so basically everywhere that we see y, we're just going to plug in that 3 over x. Okay, so if we plug it in, we get x multiplied by the derivative with respect to x of our function here, 3 over x, is equal to minus y. So that's minus 3 over x. Okay. All right, so to do a little bit of differentiation here, this would be a good refresher of how to take derivatives of a function where x is in the denominator. Okay. And so if we apply this derivative here, right? So you have derivative of 3 over x, that's basically the same as the derivative of 3 times x to the minus 1 power. Okay. And so if we apply our simple power rule here, we get the derivative of this is equal to minus 3 times x to the minus 2 power. Okay. All right, and so if we just kind of plug that in and we just do the multiplication there, we have x times minus 3 x to the minus 2 is equal to minus 3 over x. And so we just perform this arithmetic. We have an x that's going to cancel out with 1 in the denominator. So this x here is going to cancel out with this. And so that becomes a minus 1. And so we have minus 3 times x to the minus 1 power is equal to minus 3 over x. And, we can see that these two expressions are equivalent. So we can say that this is verified. And 3 over x is indeed a solution to this differential equation. Any questions on this example here? Okay, good. Okay. So a little bit more vocabulary, a little bit more definitions before we really get rolling here. Okay. First thing I want to define, I should have defined this earlier, is ordinary differential equation. Okay. Should have defined this earlier because I'm getting tired of writing out differential equations. So now I can just write ODE. Okay. All right. So an ODE is simply just a differential equation with only one independent variable. Okay. And technically only one dependent variable too. So this is probably the only differential equation you've worked with in your previous classes, just because they're the easiest to solve. The opposite of this is what's called a partial differential equation. And so partial differential equation will have multiple dependent variables. And that means you're going to have partial derivatives in your equation, and it just becomes a much bigger mess to solve. So, we're sticking to the basics here. Okay. Okay. Another definition that I want to define here is called general solution. And so what you're going to see is that, a lot of solution procedures for differential equations involve integration of some kind, right? Because the opposite of taking derivatives is taking the integral, okay? And so oftentimes when you take an integral, you're going to be left with an arbitrary constant in your solution. So a general solution is one that still keeps that arbitrary constant. Okay. Usually for most solution procedures, for solving differential equations, you're going to obtain a general solution first. And so this is usually the first thing that you obtain when you first solve a differential equation. Okay. There are exceptions to this. And so you'll see that when we get to Laplace transforms. So Laplace transforms when we solve a differential equations with Laplace, we're going to kind of just bypass the general solution altogether. But we'll cross that bridge when we get there. So at least for the next 3 weeks, we're just know that we're going to be solving for general solutions first. Okay. Next definition is a particular solution. And so particular solution is one where you specify a value for the arbitrary constant in the general solution. Okay. Hence we call it particular. It's particular to a specific value. Okay. And so there's no longer any arbitrariness in the solution. You assign that. Okay. And usually the way that we assign a value to that arbitrary constant is that we apply some kind of either boundary condition or initial condition. So in many of the equations or differential equations that we're going to solve in this class, there will be an initial condition or a boundary condition. Or once we get to second order equation next week, you'll have multiple initial conditions. Question? Mhm. All right. Last term before we actually get to solving stuff. I know there's a lot of definitions, a lot of terminology today, but it's the first day. We kind of have to define everything. Is initial value problem. Okay. Or sometimes it's abbreviated IVP. Okay. So you'll see this term come up a lot, especially in engineering contexts. So an initial value problem is nothing more than just the combination of a differential equation or an ODE together with all of the initial and boundary conditions. I'll say it's just initial conditions. So technically there's a problem called the boundary value problem, which you supply all the boundary conditions, but this is just initial value problem. So it's initial conditions. Okay. Mathematically, there's not that much a difference between initial conditions and boundary conditions. In fact, they're applied in exactly the same way. So you'll probably hear me use the terms interchangeably throughout the class, but physically, obviously, there's differences between them. Initial conditions are applied in the time domain and boundary conditions are applied in the space domain. But, for our purposes, they're all kind of the same. Okay. All right. Any questions on this? Okay. All right. So let's actually get to solving some differential equations. So in terms of first order equations, there are two categories of equations that we're going to solve. The first one we learn is called separable ODEs. Okay. All right. And so a separable ODE is one where we can do what's called separation of variables. And so the structure of the ODE is such that, you can take everything that depends on the independent variable, put it on one side of the equation, and everything that depends on the dependent variable and put it on the other side. Okay. Okay. All right, so mathematically, it looks something like this. And so the general form for a separable equation is g of y multiplied by dy dx is equal to f of x. Okay. Right. Where the most important parts of this is you can see that this g of y is some term or some expression that depends only on the dependent variable. Okay. And this f of x here contains only the independent variable. Okay. All right, and so the equation is structured so that you can kind of separate these two. It may not be apparent at first, but you can also perform algebraic operations, just simple kind of adding, subtracting, dividing in order to get it into this form. Okay, because what we can do, if we have the equation in this form, actually, I'm gonna go tell them to shut up. Hang on. We got. Probably have to do that again in 20 minutes, but at least I slowed them down for now. Okay. All right. So why would we want to do this? Why would we want to separate the variables? Well, we can do this because in this form, we can perform integration very easily because, even though, I've been told by math people, I had a good friend in grad school that was a math major. This is mathematical sacrilege, but, what you can do is you can just take this dx and just push it over here. And so if we do that, we get g of y dy is equal to f of x dx. Okay. And why would we want to do that? Well, now we can just simply integrate. Okay. So separable equations are nice because, it kind of, we don't, in some sense, you don't really need any specialized techniques. And so if you know how to perform integration, you can solve a separable equation. Okay. Okay. All right. And so the important thing to note here, kind of going back to our definitions from just, 10 minutes ago, these integrals here are, indefinite integrals. And so what that means that, there's no integration bound. So when we perform these integrals, didn't even last 20 minutes. So when we perform these integrals, we have to add an arbitrary constant at the end. Okay. Okay. Okay, so let's do an example. I think that will kind of make things a bit more clear. Okay. Okay, so we'll do one where we don't have any initial condition. We'll just solve for the general solution, and then we'll do another example where we do have an initial condition. Okay. Okay. All right, so let's find the solution to this ODE. Okay. So you have dy dx is equal to 1 over 1, or excuse me, dy dx is equal to 1 plus y squared. Jumping ahead a little bit. Okay. All right, so let's go ahead and solve this using separation of variables. So in this form right now, the variables aren't separated, right? So on the one hand, we have dy on the left-hand side, and we have an expression here that contains y on the right-hand side. So let's perform some simple algebra. So let's divide both sides by 1 plus y squared. Okay. And so if we do that, we get, and let's go ahead and move the dx over to the right-hand side while we're while we're doing this too. And so we have dy over 1 plus y squared is equal to dx. Okay. All right. And so if you look at this equation here, on the left-hand side, we have everything that's involving y. On the right-hand side, we have just 1 multiplied by dx. And so technically, that's an expression we can integrate as well, right? Now that we have in this form, we can just simply integrate. Okay. All right, so if we perform these integrations here, so we take the integral of the left-hand side, dy over 1 plus y squared. This is a special integral here, and so this is not one you could solve by u substitution. This is one that you kind of just have to memorize. So this, which what? Yes, exactly. So it's arctangent of y, or tan inverse of y. Okay. Okay. All right, so let's go ahead and add our arbitrary constant, because remember, this is an indefinite integral. And on the right-hand side, we have basically integral of 1 dx, and so that's going to give us x, okay? And we have to add our arbitrary constant there as well, okay? So we have c1 on the left, c2 on the right. All right. So, we performed our integration here. We have our arbitrary constants. To make our life a little bit simpler, because we haven't assigned any values for these constants. So c1 and c2 could be anything. So since c1 and c2 are both arbitrary constants, let's just merge them together into one, just to make our lives a little bit easier. Okay. So since these are still arbitrary, so let's define a new constant. So we'll call this capital C. Okay. So capital C will be C2 minus C1. The exact definition doesn't matter as long as you have at least one arbitrary constant somewhere in this expression. Okay. And so if we plug that in, we get tan inverse or arctangent of y is equal to x plus capital C. Okay. All right, so you'll see me do this step quite a bit. A lot of times our solutions will be, you'll have multiple arbitrary constants, but if you can combine them, usually it's better to do that just so you have less things to solve for. Yeah. Okay. There will be situations where you can't combine them, and so you'll see those in our second order equations. But usually, the number of arbitrary constants that you have is equal to the order of the equation. So for first order equations, you're only going to have one arbitrary constant. For second order equations, you have two arbitrary constants. If you're getting more than that, you can probably combine them into that. Okay. All right, and so if we want to solve for y here, it's pretty simple. It's a pretty simple case. So let's just take the tangent of both sides. Okay. And then we finally arrive at our solution. And so our solution here is y of x is equal to tangent of x plus c. Okay. And since this solution here is still subject to an arbitrary constant, we can say this is our general solution. Okay. All right, any questions on this example here? Okay, good. All right, let's do another example, because that one, you know, we had to do kind of a, we had to pull out kind of the tan inverse integral. So this one's going to be a little bit more typical, I would say. Okay. This one will also have an initial condition. So we can actually solve for arbitrary constant. Okay. So let's solve for the solution to this equation. So we have dy dx is equal to minus 2xy. Okay. And then we're going to have an initial condition. And so, you know, usually the terminology that we use is that, you know, we present a differential equation and we say this differential equation is subject to some initial condition. Okay. So the initial condition in this case is y of 0 is equal to minus 1.8 or positive 1.8, excuse me. Okay. And so we're going to use that initial condition to solve for the arbitrary constant after we obtain the general solution. Okay. All right, so let's go ahead and start solving this. And so, you know, we need first thing we need to do is we need to separate our variables here. All right. So first thing we can see is that on the right-hand side, we have minus 2xy. Okay. We want to move the y term over to the left-hand side because that's where the derivative is. And so let's go ahead and move this over. Right. And the way that we're going to do that is we're going to divide both sides by y. Right. So since we have an algebraic equation here, we have to use an algebraic you know, operator in order to get it to the form that we want. Okay. The other thing that we'll do is we'll kind of multiply both sides by dx. Okay. So we're going to move the dx over to the right-hand side. And so we do both of those things. We get y dy is equal to minus 2x dx. Okay. Or excuse me, 1 over y. Because we divide by, we didn't multiply by. All right, so let's take a step back and let's kind of look at our equation here. We can see on the left-hand side, we have everything that's a function of y, which is our dependent variable, and everything on the right is a function of x, which is our independent variable. So we've successfully separated out the variables. Okay, okay, so let's go ahead and perform our integration. Okay. All right, so left-hand side, we have integral of 1 over y dy. And on the right-hand side, we have integral of minus 2x dx, okay? Integral of 1 over y is the natural logarithm of y. Okay. And so I'm not going to put an arbitrary constant on that side. I'm just going to put it on the right-hand side as 1, okay? And then on the right-hand side, we have integral of minus 2x dx. That is minus x squared. And then to this, we're going to add our arbitrary constant of c. Okay. Okay. Good. All right, so let's go ahead and solve this. So first thing we're going to do is we're going to isolate y. And so we need to kind of get rid of the natural logarithm. So the way that we get rid of natural logarithm is that we raise it to the power of e. Okay. Okay. All right, so let's go and do that. So we're going to raise the left-hand side, e to the power of that. And on the right-hand side, we have e to the power of that as well. Okay. So the e and the natural logarithm are going to cancel out. And so that's going to successively solve for y. And so on the left-hand side, we have y of x. Okay. Perfect. And on the right-hand side, we have e to the power of minus x squared plus c. Right, so that right there is our general solution. So we've solved for y, we've isolated it, and we have our expression for x on the right side. Okay. Now, to make our life a little bit easier, we can simplify this arbitrary constant. Okay. Because if you remember the rules of exponentiation, if you have the addition of two terms in the exponent, You can multiply them together. So we have e to the minus x squared multiplied by e to the c, okay? So those two terms, e to the minus x squared plus c is equal to e to the minus x squared times e to the c, okay? We know e here is just a number. It's a very irrational number, but technically it's a number. So if you have a number raised to the power of another number, the result of that is a number, right? Exactly. So we can just replace this with another constant. So typically we use a. And so this is equal to a multiplied by e to the minus x squared. Okay. So now instead of solving for something that's in the exponent, we're solving for just a coefficient in front, which is typically a lot easier to do. Okay. Okay, so this right here, this is our general solution. Now let's go ahead and apply our initial condition here to solve for the arbitrary constant. Okay. Okay, so let me write down the initial condition again, just to kind of recall. Our initial condition is y of 0 is equal to 1.8, okay? Another way to express this is that the value of y when x is equal to 0 is equal to 1.8, okay? And so to apply this initial condition, we're basically going to plug in x is equal to 0 into our general solution, set the entire equation equal to 1.8, and then use that to solve for a. Okay. Okay. All right, and so if we do that, we get y at x is equal to 0 is equal to a multiplied by e to the minus 0 squared, and all that's equal to 1.8. Okay. All right, and so we have a very simple algebraic equation here, which we can solve for a. So we have e to the minus 0 squared. 0 squared is 0, minus 0 is 0. E to the 0 is just 1. Right? So from this, we get a is equal to 1.8, which is exactly the equation that we need. Okay. So now that we have a value for a, let's plug that value of a back into our general solution to get our particular solution. So our particular solution in this case is y of x is equal to 1.8 multiplied by e to the minus x squared. All right. Any questions on how we got this result here? Okay, good. All right, 30 minutes to spare. Perfect. Okay, so last thing we're going to go over today is the solution to linear first order differential equations, which are going to perform using integrating factors. Okay. So separation of variables, I would say is a good first technique to learn when you're solving differential equations, but it's not the most practical. So there's not too many engineering systems that kind of fall into the separation of variables category. But it's a useful one to learn first. I would say linear ODEs are much more common. In fact, the differential equation we saw earlier in the class today, Newton's law of cooling, falls into this category of linear ODEs. Okay. So let me write the general form for a linear ODE or linear first order ODE. Okay. So the general form for these equations is dy dx plus p times y, or I should say p of x times y, excuse me, is equal to r of x. Okay. And so you can see here we have our dependent variable is still y in this case. We have the derivative of y plus some function p of x multiplied by y itself is equal to r of x, and r of x does not contain anything of y. Okay. So first thing you should see here is that, because we have that addition on the left-hand side, this is not an equation that we can separate, at least not in this form, right? So this is not a separable equation. And so we're going to need to use another technique to solve it. Okay. Okay, let me point out a couple other kind of characteristics of this equation here. Okay. First thing to address, I think, are these coefficients here. Okay. So p of x and r of x. Okay. Notice how these do not contain y at all. So these are functions strictly in the independent variable, or they might be constants. Okay. So that's really important. And so, it's important that these coefficients and these terms do not contain the dependent variable y, okay? Because what would happen? So if we look at p of x specifically, if p of x had some kind of function of y attached to it, then we're going to end up with y to some power other than 1, right? Because if you look at this y by itself, right, technically this is y to the first power, right? But usually when something is raised to the first power, we don't put the 1 there. It's just kind of assumed, right? And so whenever you have a term with the dependent variable raised to some power other than 1, then you have what's called a nonlinear equation, right? But in this case, is both of the times when the y appears, where it's in the dy dx, and in the second term, the y, okay? In both of those situations, the y appears with an exponent of 1. Right. And so that characteristic right there, I think, for a lot of times it's kind of easy to miss, or it's kind of easy to take for granted. This is what makes the equation linear. And so when you say that, we have a linear equation, linear, all that means is that, whatever your dependent variable is, whatever your unknown variable is, it only has exponent of 1 in the equation. Okay. So this concept of linearity actually, it's actually very consequential, because there's basically a way that you solve a linear equation, and there's very different and much more difficult ways for you to solve nonlinear equations, right? So for our class, we're going to stick to linear equations, but just know that there are techniques for solving nonlinear differential equations. Those are just, way beyond the scope of this course. Those are kind of graduate level courses, and even grad students and even myself are scared to solve nonlinear equations. That's how That's how bad it is. So, but we'll stick to minis. Okay. Okay. All right. So one other thing I wanted to point out for this equation is that if you notice the coefficient in front of the derivative term, the only derivative term is 1. Okay. Again, it's not something I explicitly put there, but you have 1 multiplied by something. It's the same thing as that something. And so this is important because this is what's called standard form. Okay. So whenever you have the coefficient of the derivative term with a coefficient of 1, that's standard form. And we'll come back to this concept of standard form because we do need to solve our higher order equations as well. Okay. Right. And so actually, let me make the definition a bit more general because, we're going to come back to this in second order. So whenever the coefficient for the highest order derivative is 1, that's known as standard form. Okay. All right. So now that we've kind of dissected this equation and we kind of looked at it from multiple different angles, let's actually get to solving. Okay. Now, the way we actually solve this equation is actually interesting. You could make the argument that, differential equations as a whole is a very interesting math topic because, in some ways, when you solve a differential equation, with the exception of separation of variables is, I would say, kind of more true math. A lot of times when you solve differential equations, you kind of have to rely on, I kind of call them, kind of cheap party tricks. Okay. Because, there's no way that we can directly integrate this equation in the way that it is. Okay. A party over there. Okay. Right, because we can't really separate out the variables. We can't pull out the dx from this. We can't separate the dy. We can't directly integrate that. But we really like direct integration because direct integration is simple. Okay, so the way to actually solve these linear equations is we're going to manipulate this equation in a way such that we do get something that we can directly integrate. All right, and how would we do that? How would we manipulate this equation to be directly integrable? Well, the way that we're going to do that is we're actually going to make the equation more complicated than it is. And so we're going to actually multiply it by another factor called the integrating factor. Okay. All right, so let's see what that would look like. So let me go ahead and write out our linear equation one more time, and then we'll work on, we'll work on the integrating factor. Okay, so if we write out the equation one more time, we have dy dx plus p of x multiplied by y is equal to r of x. All right, so like I mentioned before, this equation as it is right now, we can't really do anything to it. It looks relatively simple, but, we can't solve for y. And ultimately, that's what we want to do, right? Okay. So what if we made this equation more complicated? So let's multiply the entire equation. Okay. We're going to multiply the left-hand side and the right-hand side. So all three terms, we're going to multiply it by another function, which we call the integrating factor, mu of x. Okay, so let's go ahead and distribute that through. So we're just going to, apply this to every term here. So we have mu of x multiplied by dy dx plus mu of x multiplied by p of x multiplied by y is equal to mu of x r of x. Okay. We've taken our relatively simple equation and we've kind of made a mess of it. But, from this mess will become something beautiful, I promise. Okay. All right, so we're mostly going to focus on the left-hand side because, if you look at the right-hand side is actually already in pretty good shape. So the right-hand side, you have one function of x, which is just a function of our independent variable, multiplied by another function of our independent variable. So the right-hand side, actually, we can technically directly integrate that already. So, we're not going to worry about that. We're going to focus mostly on the left-hand side. Okay. And so on the left-hand side, we can see we have this form here. So we have mu multiplied by dy dx plus mu p times y. Okay. If we kind of go back into our memory banks in terms of differentiation rules and all just the random stuff you learned in Calc 1, Calc 2, we can say that this kind of looks familiar. Right? Okay. 20 minutes. Okay, 15 more minutes. And then I'll go tell them to shut up again. Okay, so we say this looks kind of familiar. And so I'm gonna bring up probably a character that you didn't expect to see today, or maybe if you know integrating factors, you're kind of already expecting this. Let's bring up the product, right? Okay, so what was product rule? So product rule is basically if you have two functions that are multiplied by each other and you take the derivative of them together, then you get a certain expression, right? So let's do this. So let's take the derivative, d dx, and let's take the derivative of our two functions here that are functions of x. So let's take a derivative of mu multiplied by y of x. Actually, that's fine. Okay. So we have the derivative of the product of mu of x and y of x. Okay. I didn't forget about p of x. P of x is going to come back in a second, but this is kind of just an aside. Okay. Okay, and so if we do our product rule, if you remember how this works, you have basically derivative of two functions multiplied by each other. You have derivative of the first function multiplied by the second function, and then derivative of the second function multiplied by the first function. Right? So you have d mu dx, that's derivative of the first function, multiplied by the second function, which is y, plus mu multiplied by derivative of the second function, which is dy dx. Okay. I'm going to go ahead and swap these two just because, addition is commutative. So you can swap the order. So I'm going to put this is equal to mu dy dx plus d mu dx multiplied by y. Okay. All right. So the reason I swapped these is that, let's compare this expression that we got with our original left-hand side, right? Okay. So that's why I said that left-hand side there looks kind of familiar because you can see how things will start to match up a little bit, right? And so if you look at this first term, this mu dy dx, these are exactly the same, right? And so, it seems like we're kind of onto something here. And so, it kind of seems like it was a good idea to kind of recall product, right? So that's good. That means we're on the right track. The second term is not quite the same, but it is something we can work with, right? And so let me go ahead and write both of these down here. So we have mu of x, e of x times y, and d mu dx times y, okay? Right, so that's the only difference between our product rule and our original linear ordinary differential equation, okay? So the most important part here is how they both depend on y. And so if you can see, this has a y here and a y here, okay? And so what if we did this? What if we said that the coefficient in front of y, these two are the same, right? So if we say that mu of x, p of x is equal to d mu dx, okay? Right, so if we set these two equal to each other, then our original linear differential equation is equal to our product rule that we just kind of made up and just kind of pulled out of our ass, right? Okay. And why would we want to do that? Why would we want to make things equal to our product, right? Well, if we did that, so if this relationship were to hold right here, so we have this relationship mu p of x is equal to d mu dx, right? Then what we can do is we can substitute this back into our original equation, okay? And so if we do that, then what you can see here is that if we were to do that, then what we would have is a separable equation, one that we can directly integrate. Okay? So if this were a substitute here, then what we would have is a directly integrable equation. Okay. And that's good. You know, we want to be able to directly integrate because then that gives us a way to solve these equations. Okay. Now, the key to all this, of course, is our integrating factor. So, you know, this mysterious function mu, you know, if you notice up until this point, we haven't actually specified any rules for it. It's just a random function that we just pulled out of somewhere and multiplied by our equation. Okay. And so in order for us to solve an equation with integrating factor, the integrating factor has to follow this specific relationship right here. Okay. So this relationship gives us a way to solve for our integrating factor. Okay. Which, if you notice, is another differential equation. But you know, one thing about this differential equation you can see is that it is separable, and so it doesn't have the original linear form. This is one that we can solve by separation of variables. When I was in high school, there was a show that I would watch after school every day called Pimp My Ride. And so kind of a meme that came from the show that says, you know, well, the whole show is about taking an old kind of beat up car and making it kind of fancy. And so one things that they would always interview the guests and say like, oh, like what kind of things do you like? And they're like, oh, you know, I like playing poker or something like that. And so the host of the show he was a rapper named Exhibit. He's like, oh, we heard you like poker. So we put poker inside your car. He's like, whoa, crazy. So this is the same thing. So it's, you know, we heard you like differential equations. So we put a differential equation inside your differential equation. So you can solve two equations at the same time. So that's kind of how this thing works. So, you know, let's pause here and let's actually do let's do an example. There's faster ways to do this, do these types of problems because you can kind of just go straight from the expression. So if you were to continue on with this proof, you do get an equation you can plug into. And that equation is in the notes if you do want to see. Maybe we'll probably come back to it on Tuesday.
speed.
Yeah, so but I did want to work through an example to kind of show you the logic in terms of how this entire thing works. Okay. So one last example before we head out for today. Okay. Okay, so let's do an example from electrical engineering. So let's do a simple RL circuit with the DC value. Okay, so this a very simple circuit. So we have basically the RL, the R stands for resistance, the L stands for inductance. Okay, so we have our resistor here that has a resistance R. This is connected to an inductor, which is basically a coil, has an inductance L. And this entire circuit is driven by a battery. And we're saying this is a DC battery, and so the amount of voltage that the battery is producing is going to be constant. Okay. Okay. So we're not going to go through the derivation of the governing equation here. That's for a circuits course. But if you were to apply the circuit laws here, Kirchhoff's laws, you would obtain the following differential equation. So the governing equation is di dt, where I here represents the electric current that's going on in the circuit, okay, plus R over L multiplied by I is equal to the voltage on the battery divided by L. Okay. Okay. So you can see from this differential equation here, we have an equation that's not separable. So it's impossible for us to do separation of variables here just by strictly algebraic means. And so we have to solve this equation using integrating factor. Okay. All right, so let's go ahead and solve this, and then we'll pack it up for today. Okay. All right, and so if we compare this equation to our general form, right? So remember, our general form of a linear equation is dy dx plus p of x multiplied by y is equal to r of x. Okay. So this example is good too, just to show that there's nothing really special about the letters y and x. You can replace those with whatever the variable names are, right? And so in this case, our independent variable is time t, and our dependent variable is the current I. Okay. The R, the L, the E, those are all just constants in this case. Okay. Okay. And so from here, we can just kind of match up the terms. So we can see that, I is equal to y, t is equal to x, our p of x is equal to r over L. Okay. And our r of x is equal to e over L. Okay. Okay. So first thing we're going to do is we're going to solve for our integrating factor. Okay. So let's use our expression for the integrating factor that we had up above. Okay. So our expression for the integrating factor was p of x multiplied by mu of x is equal to d mu dx. Okay. Let's go ahead and plug in our terms for this particular equation here. So p of x is r over L, which is just a constant. Okay. So you have r over L. Okay. We don't know mu of x, but also, we can substitute t for x. And so this is mu of t. That's our integrating factor. Okay. And that's equal to d mu dt. Okay. Okay. All right. So let's go ahead and perform this integration here. So this is pretty simple. And so we're going to separate the variable. So we're going to move mu of t. We're going to divide both sides, put it in the denominator. We're going to move dt to the other side. Okay. And so we have R over L multiplied by dt is equal to d mu over mu. Okay. Now we've separated the variable, so now we can perform our integration. Okay. All right, so we perform our integration, and what we get is R over L multiplied by T is equal to ln of mu. Okay. Right. So normally at this point, we have to add our arbitrary constant, but for our integrating factor, since this is just, it's not our original equation, we can kind of skip the integrating factor, or we can skip the arbitrary constant. It doesn't really affect our solution anyway. So we can just take we can exponentiate both sides, solve for mu. We get mu of t is equal to e to the r over L t. Okay, good. So now that we have an expression for the integrating factor, let's go ahead and multiply this by our original equation. Okay. So our original ODE is we have di dt plus r over L times I is equal to E over L. Okay. So we're going to multiply both sides of this equation by mu of t. Okay. And so if we do that, then we get mu of t. Let's just plug in for mu of t, since we already know what it is. So mu of t is E to the R over L times t times di dt plus E to the R over L times t times R over L times I is equal to E over L, E to the R over L times t. Okay. All right. So if we make this observation here, okay, we note here that this E to the R over LT, this is nothing more than mu of t. And this expression right here, E to the R over LT times R over LT, this is d mu dt. Okay. We plug that in, we get mu of t di dt plus d mu dt times I is equal to E over L times mu of t. Okay. Right. We can say that this left-hand side is the product rule. Okay. For mu of t and I of t. I apologize, I'm going to go a little bit faster so I know we're out of time. And so I'm going to write out the what the product rule is, and then we'll kind of pick this up on Tuesday. Okay. Okay. And so if we apply the reverse product rule to this, we can say that that left-hand side is equal to d dt of mu of t multiplied by I of t is equal to E over L mu of t. Okay. All right, and so we've basically taken our linear ODE, which was not separable, and now we've turned it into something that we can separate and integrate. Okay. Okay. And so when we come back on Tuesday, we'll finish up this problem. We'll actually perform that integration. We'll see how that looks. We'll do one more example so you can kind of see how this works, and then we'll move on to second order equations problem. Okay. All right, so thank you everyone for coming today. I apologize for going a bit over time. I hope you all have a good weekend, and I will see you guys on Tuesday.
Or if you could scroll up a little bit,
Sure.
I'd like to miss the lines. That lines, yeah.
Want me to grab more? Is this good?
No, that's good.
Okay.
Thank you so much.
It's that quick version, that's P, Q, and I, and you let different parts of the equation.
Yeah.
Yeah.
Well, basically, the quicker version, we kind of finish out that proof. You get one equation, you can just plug into the equation,
Yeah.
plug in for P and I and stuff like that.
It's like 1/I times the integral plus the arbitrary.
Exactly. Yeah. But I like to go through kind of the whole logic just so you kind of know is, because if you just look at the equation, you're kind of just plugging and chugging. But I think with this, you actually kind of, you should kind of understand why we kind of do everything the way that we do. Yep,
I'll email you all.
sounds good.
Have a good weekend.
You too?
And so I actually, my FEA class is at 5:30.
Okay.
And I talked to the professor. I didn't talk to the professor, actually. I heard him and he basically said that this semester we're like not even gonna have ANSYS at all.
Oh, okay.
It's all gonna be theory. So
I
I'm
see.
like, I don't know if I want to take it.
I see.
But a friend of mine is actually in your graduate level course.
Okay.
And he was like, dude, I've never taken an FEA course and I'm able to take this. So I'm like, okay. I was wondering if I can just kind of sit in and kind of see how that is.
You can, yeah. So the graduate course I'm teaching this semester also going to be predominantly theory. We do a little bit of ANSYS, but
Yeah.
But I have another graduate course, 540 that I'm not teaching this semester. That one is the ANSYS course. But the one I'm teaching this semester, 541, this is the primary
What
theory.
is your 410 class that you teach?
It's kind of a mix of both because the 410 is kind of like, for most undergrads, that's the only exposure to FEA.
Yeah.
For grad students, usually they're going to take both, and so they have the ANSYS course and the theory course. But for the 410 course, I kind of have like, it's probably like,
Yeah.
like 50-50, I would say 50% ANSYS, 50%.
You basically told us like, look, guys, like we're just gonna be doing theory and probably the last week we'll probably touch on ANSYS.
I see.
I
I see.
don't want to take the course. So.
Yeah, I mean, that's honestly, that's probably more traditional in terms of like your first FEA course. But I did modify it to include more ANSYS. Like when I first taught it, it was based kind of like that.
It was like that.
But I know there's a bit of demand for ANSYS, especially, if you're gonna use it for your projects and stuff like that. So I did, yeah, so I did modify it, but the way he's teaching it is honestly, that's more traditional.
Is it possible for me to kind of be able to take this course, or is there kind of no way as an undergrad student?
You can take the course. Although because it's a grad course, you do have to get kind of blessing of the instructor, which is me.
Yeah.
But usually I only let undergrads into 541 if they had already taken 410. Oh, because we are going to do pretty heavy into the theory, and so I like to kind of see that beforehand, or at least be a grad student so that I know you can kind of keep up with the math, because it can be a little bit intense with that. I mean, you're free to kind of come in and see. But yeah, I would like, normally I would like for you have taken the 410 before 540.
Okay,
Yeah.
got it. Yeah, because I'm like, the reason I'm taking it, I really want to be able to use, as a gun, I want to be able to use ANSYS for my senior project.
Yeah.
So I was like, I can just learn it off the fly by myself, but like, I don't want to do that.
You can check out my YouTube lectures, and so if you go to my YouTube, so I'm posting everything from my SIG YouTube channel, and I have a playlist there for 410.
Yeah.
So all of the ANSYS tutorials I do are on there, and so you can kind of, I've had, I don't know if you know Johnny. Johnny kind of self-taught himself ANSYS over the summer. He just looked at my lecture. So I mean, there's that. I mean, you can kind of take 410. I would say, maybe stick with 410 as it is right now, learn the theory, and then you can use the video lectures to learn the ANSYS.
I was like, maybe I'll just wait till next semester and just take it with you. Like, if you're offering, I was like, I don't.
Yeah, I mean, typically we'd offer in the fall. I don't know if I'll be teaching it, because Dr. Wang can teach 410 now too.
Okay.
But it'll definitely be offered. Okay, all right, maybe it'll be.
Dr. You teach the course, do you go like 50-50, like ANSYS and theory?
Oh,
Dr. Wang,
Yeah, she.
sorry.
do you go like 50-50, like where you like teach ANSYS?
No.
Okay.
We have 4 in-class practices plus 6 hands-on homeworks.